welcome to my classroom. Yesterday I think you have prepared with the video what I have sent with the content that is the Alfven theorem and one problem based on that. So I think you have prepared. Today I am going to do the different concept, that is the Kelvin circulation theorem. Here we have to prove, in MHD we have to prove the Kelvin circulation theorem is not valid. But in fluid mechanics, I think you may remember that you have proved the Kelvin circulation theorem as the rate of change of circulation is constant, means d gamma by dt is equal to 0. But here it is not possible because, so there we proved the theorem in the absence of magnetic field. In MHD there will be magnetic field, means Lorentz force. That's why the Kelvin circulation theorem is not valid, means we have to show d gamma by dt not equals to 0. And also we have to derive the Helmholtz equation in MHD. You have derived Helmholtz equation for vorticity in fluid mechanics. There you showed that equation is given by d by dt of omega by rho is equal to omega by rho dot del of q. But here, whatever the role of omega by rho, so the magnetic field satisfies the same equation. Means instead of omega by rho, if we take h by rho, then Helmholtz equation satisfies d by dt of h by rho is equal to h by rho dot del of q. Means the magnetic field satisfies the Helmholtz equation. Now let us see how to prove the theorem and how to derive the equation. Please come to my... Okay, come to Kelvin circulation theorem. Kelvin circulation theorem. Okay, so here we have to show the Kelvin circulation theorem is not valid in MHD. Okay, so you know, in fluid mechanics you proved that the rate of change of circulation is 0, means there we have proved d gamma by dt is equal to 0, where gamma means the circulation is given by line integral over the closed contour C of q dot dl. Okay, so this is the gamma definition of circulation. You have studied already in fluid mechanics in third semester. So there, for the Kelvin circulation theorem, we proved that d gamma by dt is equal to 0. Now we have to prove in MHD the Kelvin circulation theorem is not valid in MHD, means we have to show d gamma by dt is not equals to 0. Okay, now consider the circulation, definition of circulation, that is gamma is equal to line integral over a closed contour of q dot dl. Okay, it implies d gamma by dt is equal to, so what you will get, line integral over c of dq by dt dot dl. Okay, call this equation as number 1. By differentiating with respect to t, you are going to get this equation and call this equation as t. Now consider the momentum equation, that you know, rho into del q by del t plus q dot del of q is equal to minus gradient of p plus rho into g plus mu into j cross h. Okay, so I am going to neglect the viscous term because we have not considered the term in circulation theorem in fluid mechanics also. That's why I am going to not consider that term. Simply consider this equation. Here, using the Eulerian derivative, you can write this term as, so dq by dt. Okay, and I am going to send this rho to the right hand side, then it will become minus 1 by rho into gradient of p plus g plus mu by rho into j cross h. Is it right? J cross h. Okay. You know, the Ampere's law states that the Ampere's law in the electrodynamics, you know that J is equal to del cross H. Ampere's law says that J is equal to del cross H. Using this, you are going to get J cross H is equal to del cross H cross H. Do you understand? So I want this J cross H. You know from Ampere's law, J is equal to del cross H. By substituting instead of J, you are going to get del cross H. Okay, call this equation as number 2. Now, you know one of the vector identity, that is gradient of dot product of two vectors. Gradient of dot product of two vectors is equal to, so what do you know? A dot del of B, okay, plus B dot del of A plus B cross, so, right, okay, no problem. B cross del cross A plus A cross del cross B. Okay, curl of A, curl of B, right? So this is the vector identity, you know. So by using this vector identity means by substituting, so A is equal to vector B is also equal to, so vector H means magnetic field. If we replace vector A and B by the magnetic field, then this equation will becomes gradient of H dot H means H square is equal to H dot del of H plus H dot del of H, okay, plus H cross del cross H plus H cross del cross H. Is it right? Okay, so this is 2 times and these two becomes 2 times. Therefore, so gradient of 1 by 2 H square, I am going to cross multiply the 2 times to left hand side, is equal to H dot del of H plus H cross del cross H. Is it right? Now, by by rearranging the terms, you are going to get del cross H cross H, because you know I cross J is nothing but minus J cross I. That's why if I am going to interchange these two vectors, instead of writing H cross del cross H, if I am going to write del cross H, then you will get negative sign. By taking to this side, that will become positive. It's equal to, so H dot del of H minus gradient of 1 by 2 H square. So therefore your equation 2 will becomes, using this, your equation 2 will becomes, instead of del cross H, you can write it as J cross H, but that expression is replaced by, this is nothing but your J cross H, because you know del cross H is nothing but your J cross H from equation 2. That's why J cross H can be written in this form. Now substitute J cross H in equation this one. Okay, so substitute J cross H in the momentum equation, then this equation will becomes, got it? I am going to replace J cross H in the momentum equation by these two terms. Then your equation will becomes del Q by del T is equal to minus 1 by rho into gradient of P plus acceleration due to gravity G plus mu by rho into H dot del of H minus gradient of 1 by 2 H square. Okay. Now simplify this equation. Before going to simplification, you know the acceleration due to gravity is conservative in nature. So conservative in nature means you know how to write that vector. You can express the vector g as gradient of some scalar, omega or phi, anything, okay? You can express the gravity acceleration due to gravity in terms of gradient of some scalar because this is conservative in nature. That's why you can write it as gradient of some scalar, and that scalar is known as gravitational potential. What you call? You call phi as gravitational potential. Gradient of gravitational potential is nothing but your acceleration due to gravity. Now this equation will becomes dq by dt is equal to dq by dt is equal to minus 1 by rho into gradient of p minus, okay, gradient of phi because I replace g by gradient of pi minus mu by rho into gradient of 1 by 2 h square. I have taken this term, you know, this term to that side, okay, this term to that side, and remaining is mu by rho plus mu by rho into h dot del of h, okay, h dot del of h. Further, you know, the concepts like the flow is barotropic and also frozen inflow condition. You have proved what is barotropic, okay? So in fluid mechanics, the concept of barotropic says that pressure is proportional to density, means pressure is a function of density only, the barotropic, okay? If the frozen inflow condition says that magnetic field is directly proportional to density, means h is a function of density only. Yesterday only we proved it. So the pressure is a function of density, the magnetic field is a function of density only. By using these two concepts, you know, in fluid mechanics you can write minus 1 by rho into gradient of p as minus integration of, so gradient of p by rho, okay, gradient of p by rho. I mean you can take the gradient outside, so not inside, so you have to take gradient of minus gradient of p by rho, dp gradient of p by rho. In the similar manner, so you can dp by rho. In the similar manner, you can express 1 by rho into gradient of h as, so minus gradient of dh by rho, okay? So this is due to frozen inflow condition and this is due to the barotropic condition, okay? Now this equation will becomes, using this concept, this equation can be written as dq by dt is equal to minus, so gradient of dp by rho plus minus gradient of phi minus gradient of integral of, so d by d, the derivative of 1 by 2 mu into h square divided by rho, okay, plus the remaining term as it is mu by rho into h dot del of h, okay? Now see here, so here in all these three terms you can take gradient outside, minus gradient outside, minus gradient of integral dp by rho plus phi plus integral derivative of 1 by 2 mu into h square divided by rho, okay? So plus mu by rho into h dot del of h, okay, h dot del of h. Now your dq by dt will becomes this form. Now substitute this in the equation 1. The equation 1 says d gamma by dt is equal to line integral over a closed curve C of dq divided by dt, dq divided by dt dot dl. This is equation number 1. So you know it. So in the previous slide you know it. So by substituting dq by dt instead of dq by dt from these terms with these terms in equation 1, you are going to get d gamma by dt is equal to, right, line integral over c minus line integral over c gradient of integral dp by rho plus phi plus integral d of 1 by 2 mu into h square divided by rho. Okay, dot dl plus line integral over a closed contour C, I mean mu by rho into h dot del of h dot dl. Is it right? So I split these two terms into two integrals. This is one and this is one. Now, so this is like a vector. This is like a vector because you know gradient of any scalar is a vector. That's why, so this is like a vector and we have line integral. By using Stokes theorem, you can write this as minus surface integral of curl of gradient of, right, so dp by rho and the same terms dot ds, right, plus the remaining integral as it is. Now curl of gradient, again from the vector identities you know that curl of gradient becomes 0. Is it right? That's why your d gamma by dt will becomes, so line integral over c, I mean mu by rho, take it outside, of h dot del of h. Okay, look here, in fluid mechanics, you know, so there will be absence of magnetic field, means there will be absence of magnetic field means h should be vector, h should be equal to 0. If h should be equal to 0 means this term should be equal to 0, then obviously d gamma by dt is equal to 0. That's why the Kelvin circulation theorem is valid. But in MHD, there will be magnetic field. It means in the presence of Lorentz force. Lorentz force is usually non-zero. That's why there will be no chance to get h is equal to 0. Once h is non-zero, so then there will be, I mean this term should not be equal to 0. That's why, so d gamma by dt is not equals to 0. Then what it means? It means that the Kelvin circulation theorem is not valid in MHD. Okay, hence the proof. That's the proof of this theorem, right? Now we have to derive Helmholtz 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 vorticity equation. Okay, Helmholtz. Okay, Helmholtz equation in MHD. Helmholtz equation in fluid mechanics means there we have proved it as Helmholtz vorticity equation. So we proved that equation as d by dt of omega by rho is equal to omega by rho dot del of q. Is it right? So now we have to show this Helmholtz equation, this equation is true for vorticity vector. Now we have to prove this equation is also true for the magnetic field. Means instead of omega by rho, we have to take h by rho. Means we have to show d by dt of h by rho is equal to h by rho dot del of q. Right? Q, so it is unchanged. We have to, instead of vorticity vector, we have taken only the magnetic field. Means magnetic field also satisfies the vorticity equation. That is so called Helmholtz equation in MHD. We have to derive this equation. We know for a perfectly conducting fluid, the magnetic induction equation is given by del H by del T is equal to del cross Q cross H. Is it right? Okay, the magnetic induction equation for a perfectly conducting fluid as del cross Q cross H. Now, so expand this using the vector identity. Which one? The vector identity del cross A cross B. You know how to expand this expression using vector identity, that you can write it as B dot del of A plus del dot B of A minus A dot del of B minus del dot A of B. Okay, so this is the vector identity. Using this vector identity, you can express this term, that is replace A by Q and B by H. A is equal to Q and B is equal to H means the identity will becomes del cross Q cross H is equal to H dot del of Q plus del dot H of Q minus Q dot del of H minus del dot Q of H. Okay, this is the expression. Here you know del dot H is equal to 0 using what? Using solenoidal property. Okay, solenoidal property says so del dot H is equal to 0. That's why this term will become 0. Here it is not possible to take del dot Q is equal to 0. You may ask, sir, using continuity equation you can write it as 0. No, we have not considered any incompressible steady fluid. So we have not told anything. That's why it is not possible to take del dot Q is equal to 0. But so leave it as it is, and the equation will becomes del H by del T is equal to del H by del T, and I am going to take this term to the left hand side, then it will become plus sign Q dot del of H is equal to, and the remaining these two terms, that is H dot del of Q minus del dot Q into H. Okay, into H. We are not going to operate. This is simply multiplication, right? Del dot Q of H. So you can write this term as the Eulerian derivative, because you know what is Eulerian derivative? That is del by del T plus Q dot del is nothing but your Eulerian derivative, that is d by dt. D by dt can be expressed in this form. That's why so that Eulerian derivative is applied on the magnetic field. That's why these two terms combinedly you can write it as dH by dt is equal to H dot del of Q minus del dot Q of H. Del dot Q of H. Okay. Call this equation as some 1, 2, 3, anything. Now, from continuity equation, you know that d rho by dt plus rho into del dot Q is equal to 0. We proved it we reform this equation, rewrite this equation in this form in classical MHD. Okay, that's why your continuity equation can be written in this form. By this equation, you can obtain that del dot Q is equal to minus 1 by rho into d rho by dt. You can write in this form. Now substitute, replace this del dot Q in equation 1 by this term. Okay, instead of del dot Q, you can write this term. Then this equation will become del H dH by dt is equal to dH by dt is equal to, so H dot del of Q, H dot del of Q, okay, minus, here you have del minus del dot Q into H. that term can be written as minus, and here one minus is there, that will become plus h by rho into, so d rho by dt, h by rho into d rho by dt. So because this minus sign will become plus, because you can find one minus sign here and one minus sign here. So h by rho into d rho by dt. So now take this term to left hand side, then this will become dh by dt minus h by rho into d rho by dt is equal to h dot del of q. Now multiply throughout the equation by 1 by rho. You have to multiply throughout the equation by 1 by rho, then this will become 1 by rho into dh by dt minus h by rho square into d rho by dt is equal to h by rho dot del of q. You can write in this form also. Now observe here, these two terms can be written in the form of total derivative. So how do you write? You can write this as d by dt of h by rho, because by differentiating this you are going to get these two terms. That's why as a total derivative, so you can write these two terms in the form of d by dt of h by rho. This is equal to h by rho dot del of q. Okay, so look here, this is the form of, so Helmholtz equation, what we have already proved in fluid mechanics, that d by dt of omega by rho is equal to omega by rho dot del of q. Look here and observe, so here instead of vorticity vector, the magnetic field H satisfies the same equation. That's why this is the Helmholtz equation in MHD. Okay, so listen carefully, and so you have to follow the notes whatever. So I have already sent in the group. So observe the notes and observe the video, and surely you can understand these two concepts. Okay, all the best. Thank you.